Some of your derivative assignments might ask you to create exponential or logarithmic equations. Even though this is applications of logarithms, it is important to remember how to write an exponential equation because logarithms are just the inverses of exponential equations, so it'll have a lot of the same features. So here we have Sally. She invests $300 into an investment account that compounds 20% each year. Write an exponential equation that models the situation. We know that the basic form of an exponential equation, we have our a value, which is our starting amount. So for Sally, we would say y equals our a value, which is y equals 300, because that's how much she starts with. We don't know her growth rate yet, and then we raise that to x, which is just time. In this case, it'd be each year because it compounds each year. So now we just need to find the growth rate. If it compounds 20% each year, that means it's growing 20% each year, so it's growing at this rate. If you recall back in Math 1 where we talked about turning a percentage into a multiplier, this means that if I want to turn 20% growth into a b value or a multiplier value, that means I'm taking 100% of the money I had already in my account and then I'm adding 20% on top of whatever I had before. So altogether that's 120%, which if I convert that into a decimal is 1.20. So my b value would be 1.20. So this would be the equation that would model how much money she has in her account if it compounds 20% each year. Here's another application problem. A certain fast-growing yeast colony is known to double in size every 30 minutes. Suppose there are initially 8 yeast cells in the culture. Part A here wants us to enter a logarithmic equation that gives the time t in hours when there are 800 yeast cells. So here it wants us to enter the logarithmic equation. It might be easier to write the exponential equation and then turn that into the logarithmic form. So we know with our exponential equation we have y equals a times b to the x. In this case they want us to change x to t to be in time instead. So we're going to call this t instead. So now we have y. We know our a value is 8 because we initially had 8 yeast cells in the culture. So we have 8 times b to the t. Our b is our growth rate, and we know that our yeast colony is doubling in size. So that is our base. We are doubling every time. So we know our b value is 2 because we are doubling our yeast colony. However, it tells us that we're doubling every 30 minutes. Our equation frames t in terms of hours, and so we need to rewrite how much it doubles. So I can't just place t in here because that would mean that my yeast colony doubles once in 1 hour. However, it says it's doubling in size every 30 minutes, so that means it's doubling twice in 30 minutes. So because it's doubling twice, we're going to put a 2 here to say that it's doubling twice every hour, because every 30 minutes it doubles once, and so after 60 minutes or 1 hour it will have doubled twice. And so again, this is saying that I started off with 8 yeast cells, and those yeast cells are doubling twice in the hour. If I were to simplify this, this would be y equals 8 times 4t. It wants me to turn this into a logarithmic equation when there are 800 yeast cells. So I know that my y is 800. Now we just want to turn this into its log form. In order to turn my exponent into logarithmic form, I have to have just the base and the exponent by itself. So I'm going to divide both sides by 8. 800 divided by 8 is 100. So I have 100 equals 4 to the t. And now I can turn this into the logarithmic form. My base here is 4, so I know I'm working with log base 4 of 100 will give me my t. Because again, the logarithm tells me what exponent do I need or what t value do I need in order to get a value of 100. So this is what I would type into Derivita. Log base 4 of 100 equals t. And recall in Derivita that if I want to type in log base 4 of 100, I will have to write log underscore b of first number is my base, which is 4, comma, and then the second number is whatever's inside my parentheses or my log, and I had to say that equals t. So I would have to type it like this in Derivita in order for it to show up like this. All right, part B says after how many hours are there 800 yeast cells? Round your answer to 3 decimal places. So now it wants me to solve for this. Log base 4 of 100 equals t. I can use my change of base formula to solve for this. So I know that t equals log of 100 divided by log of 4. All right, and we can see if I type that in, t is about 3.321928, etc. It only wants us to round to 3 decimal places, so that means I'm going to look at the 4th decimal place, and that will determine if it rounds up or stays the same. So in this case, it would round up to 3.322 hours. So if I want 800 yeast cells, equals, then I'd have to wait for 3.322 hours. One application of logarithms is with computers. We know that if we're encoding information that's in ones and zeros, and so that's working with base 2, and so the number of bits of information to encode some number can be represented with b equals log base 2 of n. So you might receive a question on derivative where it might ask you to find how many bits are needed to encode some number. So let's say our n is 425,621. If I want to know how many bits are needed to encode this number, I can just substitute in my number for n. So now I have b equals log base 2 of 425,621. So I want to know 2 raised to what power would give me 425,621. I can use my change of base formula, so I know that b equals log of 425,621 over log of 2, and that can give me a number. This gives me about 18.699. On derivative, I might ask for it to be expressed as an integer. An integer just means a whole number, and so 18.699 is closer to 19 than it is 18, so this would round up to 19. So we would say that to encode the number 425,621, that would require 19 bits. All right, let's check out this example here. We have a telescope, and its usefulness is limited by a star's brightness and the diameter of the telescope's lens. A star's brightness is measured by its magnitude, and the brighter the star, the smaller the magnitude. So the limiting magnitude of a telescope can be calculated by using this equation here, where we have L, the limiting magnitude, is equal to 9 plus 5.1 times the log base 10 of d, where d is the diameter of the lens in inches. Wants to know what is the limiting magnitude of a 7.7 inch telescope. Round our answer to 2 decimal places. So it wants to know the limiting magnitude, which is L. L is equal to 9 plus 5.1 times the log base 10 of our diameter, and in this case, the 7.7 inch telescope is our diameter. So 7.7. I can type this in on the decimals calculator, just a regular calculator, and that will tell us our limiting magnitude. So we have 9 plus 5.1 times log of 7.7, and we know that our calculators are already in base 10 for the log, so I can just do log of 7.7, and that gives me a limiting magnitude of 13.52110027. This only wants me to round to 2 decimal places. If I'm rounding to 2 decimal places, that means I'm going to look at the third decimal place and see if that rounds this up or if it stays the same. So 13.521 is closer to 13.52 than it is 13.53. So I know that my limiting magnitude is about 13.52. All right, this one says, what diameter telescope is required to view a star of magnitude 4? Round our answer to 2 decimal places. So I need to figure out d in this case if I have a star magnitude of 4. So 4 is my magnitude, which is my L. I'm going to say 4 equals 9 plus 5.1 times the log base 10 of d. My goal is to solve for d, so let's tell the story of d. d is inside our log base 10, then it's being multiplied by 5.1, then it's being added with 9. So if I want to solve for d, I'm just going to undo each of these steps in backwards order. So I'll undo a plus 9 by subtracting 9 on both sides. 4 minus 9 is negative 5. That equals 5.1 times the log of base 10, log base 10 of d. To undo a times 5.1, I'm going to divide by 5.1. So we're going to divide both sides by 5.1. Divide both sides by 5.1. Negative 5 divided by 5.1. This doesn't give me a whole number. Like I get like a lot of weird decimals when I put it in. So I'm just going to leave it like this. So I have a full exact answer. So I'm going to keep it negative 5 over 5.1 equals log base 10 of d. To undo a log base 10, I can just do 10 raised to some power because I know logarithms and exponents are inverses of each other. So I'm going to raise both sides where these are now the exponents. So now I have 10 raised to the negative 5 over 5.1 and 10 raised to the log base 10 of d. 10 raised to the log base 10 of d is just d. So I'm left with just d equals, and then I need to do 10 raised to the negative 5 over 5.1. Let's evaluate this on Desmos. Okay, if I do 10 to the negative 5 over 5.1, I'm going to have to put that in parentheses on here. So I'm going to do negative 5 divided divided by 5.1. And I see that gives me 0.1046 roughly. So now we have a diameter that is equal to about 0.1046, and it wants me to round it to 2 decimal places. So to 2 decimal places, I'm going to look at my third decimal place, and I see that that's a 4, which isn't high enough to round it up, so I'm going to say that D equals 0.10. If I have a star magnitude of 4, that means I need to have a 0.10 diameter telescope. A different way I could have solved this equation, negative 5 over 5.1 equals log base 10 of D. Instead of undoing a log base 10 by doing 10 raised to that power, I could have just rewritten this in terms of D using my definition of a log. So I know that D equals my base 10 raised to whatever my exponent is here. So negative 5 over 51. So I have my base raised to, my output gives me my input. So I can say that D equals 10 to the negative 5 over 51. So instead of undoing log base 10 by doing 10 raised to an exponent on both sides here, I could have also just rewritten log base 10 of D by saying 10 to the negative 5 over 51 is the same thing as D. So you don't have to do 10 to that power. You could have just used the definition of a log to rewrite it in exponential form as well. Another application of exponents or logarithms involves music. So here we have the equation f of n equals 440 times 2 to the n divided by 12, and this calculates the frequency f in hertz of the nth note above a 440. The note corresponding to the frequency 2200 hertz is approximately how many whole notes above a 440? Let's round to the nearest whole number. So let's take our equation, f of n equals 440 times 2 to the n over 12. This wants us to figure out how many whole notes above a 440 is the frequency to 2200. So 2200 hertz replaces our frequency. So I'm going to say 2200 equals 440 times 2 to the n over 12. And we know how to solve exponential equations when we use logarithms. So let's get this base and exponent by itself by dividing out 440 on both sides. I have 2200 divided by 440. That gives us 5. So 5 equals 2 to the n over 12. Using the power property, I can take the log of both sides. So I'm going to do the log of 5. I have an exponential equation with my variable in the exponent, which means I can take the log of both sides to bring this exponent down. So I'm going to do the log of 5 and the log of 2 to the n over 12. So now I have log of 5. And using our power property, we can bring this n over 12 down in front. So now we have n over 12 times the log of 2. I want to get n by itself. We can tell the story of n over here. So n is being divided by 12, and then it's being multiplied by log of 2. So if I want to undo a times log of 2, I'm going to have to divide by log of 2 first. So I'm going to divide by log of 2, divide by log of 2. Now I have log of 5 over log of 2 equals n over 12. To undo a divide by 12, I can multiply by 12. So I'm going to multiply both sides by 12. And now I have 12 times the log of 5 over the log of 2. And that equals n. If I type that in my calculator, I see that n is about 27.863. And we want to know how many whole notes is it above a 440. So I need to round to the nearest whole number. So I'm going to look at the number right after my decimal place, my tenths, and I'm going to see if that's going to round this number up to 28 or if it's going to stay at 27. Since 27.8 is closer to 28 than it is 27, I know that a frequency of 2200 hertz means that I am 28 whole notes above a 440.